Hello everyone. In this video I will present a novel protocol, proof of execution, which helps to reach consensus through fault-tolerant speculation. My name is Suyash Gupta and I did this work along with Jelle, Sajjad and Mohammad at Exploratory Systems Lab at University of California, Davis. We all know about distributed databases. They help in several applications. They help in booking tickets. They help in logging and tracking records. Now, it is possible that a distributed database can come under malicious attack. Such an adversary can try to make system inconsistent and can affect availability. In 2016 alone, US lost billions of dollars due to such malicious attacks. So what is the solution to prevent such attacks? Well, one solution is to use blockchain technology. But why blockchain? Well, blockchain talks about a very simple principle. Why should one person manage all the data? In specific, blockchain tries to give everyone a right to make decisions. Blockchain promotes principles such as democracy, decentralization, authentication, and security. So, what is a blockchain? A blockchain is simply a linked list of blocks. Each block includes a hash of the previous block, and each block includes a set of client transactions. So, what does a blockchain network look like? Well, following is a blockchain network where any person like you and I can act and participate. What does it mean by blockchain providing decentralization? Basically, anyone who decides to participate in this network acts as a replica. Everyone have the same data. And what does it mean by democracy? Well, anyone who decides to participate in this network gets a right to vote. They all can participate in deciding the fate of a transaction. At the core of any blockchain application is a Byzantine fault-tolerant consensus protocol. This protocol is used by all of these applications to order any transaction sent by the client. And these Byzantine fault-tolerant consensus protocols are the focus of this presentation. In specific, we'll take a step back in time and we'll look at the first protocol, which is Practical Byzantine Fault Tolerance Protocol. This protocol allowed doing consensus among n replicas, of which at most f are Byzantine, where n is greater than or equal to 3f plus 1. To understand this protocol, we'll take a system where we have a client and n is equal to 4 replicas. Of these replicas, at most one could be Byzantine. Now, PBFT works in a primary backup model, where primary leads the consensus and other replicas follow whatever primary says. To understand this, let's say a client wants a transaction to be committed. Now, what does it do? The client sends a request to the primary. Primary assigns it a sequence number and it tells it to all other replicas by sending a pre-prepared message. Now, each replica which gets this pre-prepared message from the primary, it agrees to support this ordering by the primary, and it does so by sending a prepare message. Now, once a replica receives prepare messages from majority of other replicas, basically from n minus f other replicas, it gets a little more guarantee that majority of good replicas also heard about this transaction. So they go ahead and send a commit message. Now again, when a replica receives commit messages from majority of other replicas, it gets a stronger guarantee. The majority of good replicas have also prepared this request, and this replica goes and executes this transaction, and then they reply to the client. So PBFT works well. And but why are we discussing PBFT? Well, the problem here is PBFT requires two phases of quadratic communication, and this has acted as a bottleneck for existing system designers. To improve PBFT, there have been several existing BFT protocols, and all of these protocols require different type of entities. For example, we know about PBFT, which requires multiple phases of quadratic communication. There was another very interesting protocol, which is Ziziwa, and it expected no failures for the best case and also required dependence on clients. Then there was this interesting protocol, Hot Stuff, which did provide linear communication but had high client latencies. Then there were another interesting protocols which achieved efficient consensus but required more than 3f plus 1 replicas. There have been other designs which require trusted components, and that is where PoE comes into picture. PoE provides a three-phase linear protocol that employs speculative execution and allows out-of-order message processing without depending on any clients or trusted components. Well, to understand PoE, we'll take our similar example where we have a client and four replicas. And PoE is also a primary backup protocol. The client sends his request to the primary, and what does do is that primary again assigns a sequence number and sends this transaction to all other replicas. Till now, we're exactly like PBFT. Now, at this point in time, every replica creates a threshold share, and they send this threshold share to the primary. Now, primary collects these threshold shares. It waits for threshold shares from n minus f replica, basically majority of replicas. And then it creates a threshold signature and it sends its threshold signature to all the other replicas. Now, once a replica receives a threshold signature, it has a guarantee that this signature could only have been created once there were shares from at least majority of other replicas. Hence, this replica goes ahead and executes the request and it replies to the client. So, in comparison to PBFT, we not only removed a commit phase, because here replicas are doing speculative execution. This is just basically prepare phase. What we have done in PO is we have linearized the prepare phase and we have removed the commit phase. And despite doing this, PO works well. It is both safe and live. But how does it happen? Well, the magical ingredient in PO's design is that if client commits a transaction, then that means such a transaction will persist in time. While it is possible that replicas may be required to roll back the transaction. For example, if the primary is malicious and it equivocates, it tries to send different transactions to different replicas, then we might require some replica to roll back their state. But if a client has received messages from majority of replicas, then that transaction is final. Now, designing protocol is one thing, but we also want to evaluate it. And to evaluate PoE, we use our Resilient DB framework. Resilient DB is open source for anyone to use and download. And Resilient DB was presented as part of ICDCS 2020 and VLDB 2020. So, what is Resilient DB? Well, it's a layered system. It has layer for storage, which includes the blockchain and other metadata. It is a layer for signing and hashing. It has a layer which basically interacts with the network. And then it has an execution layer where there are different threads and queues that help to run the consensus protocol. Now, what are the results of evaluating PoE on Resilient DB? So, we use Google Cloud for our experimentation, and we use 16 core machines. And we use Yahoo Cloud Serving Benchmark, and we ran each experiment of 180 seconds, of which first 60 seconds basically were the warm-up time. So, the first graph which we'll show, it tries to measure scalability, tries to see how PoE and other protocols scale. Basically, we compare PoE against four other protocols, PBFT, SBFT, Hotstep, and Ziziva, and we scaled from 4 replicas to 91 replicas. And what we see is that PoE scales much better against all other protocols, even if there are failures. Next, we thought of seeing, do these protocols benefit if there is batching? And what we see is that that is not the case. PoE still performs better in comparison to other protocols, and it continues gaining good performance with larger batches. So, to conclude about PoE, well, PoE is a consensus protocol which achieves Byzantine fault-tolerant consensus in three linear phases. PoE employs speculative execution and out-of-order message processing to achieve higher performance. PoE guarantees that if client commits a transaction, then that transaction will persist with time. And it is possible that a replica might see a fraudulent transaction and it may be required to roll back its state. PoE supports a design where designers can also use two-phase MAC variants for achieving maybe low-cost signatures. Thank you.